What I would like to talk about in the next 20-25 minutes or so is the integration of different disciplines when somebody is trying to model complex powertrain phenomena. And the motivation of this work, of this research, has been mainly a combination of noise, vibration, and harshness studies and efficiency. And I'm very glad that this was brought up by all the speakers today, that efficiency is a very, very important issue in automotive applications, as well as NVH. So I couldn't resist of starting my presentation with a slide that describes some aspects of the physics of the problem and how the two disciplines that I'm going to focus on, tribology and dynamics, are coupled together when studying lubricated mechanisms. So in this case, we have two solids which, because of the influence of some load or some motion under the presence of lubricant, are coming together. And because of the increased load, here we have some deflection. We have some macro scale deflection here which changes the geometry, and some micro scale deflection here at the asperities of the surfaces of those two solids. And it's not only this motion, but also some relative motion that may take place here, which, added to the impacts that are taking place, is generating friction, again, in the presence of some lubricant. Now, what type of friction we have and what are the characteristics of this friction depends on the size of the lubricant that is separating those two surfaces. So we may well have situations where we have a very clear film formed between those two surfaces under light loads, and then we fall within the hydrodynamic lubrication regime of this Streiber curve, where the coefficient of friction and this parameter lambda, which is a function of the size of the film here and the surface roughness, are depicted. But as the loads increase, then there is a clear deflection of those two surfaces, change in geometry, and the coefficient of friction starts reducing. We don't have a large effect from the viscous action during the generation of friction in the contact, and now the surfaces are coming very close, and we have the generation of what is called boundary friction there. So this is the mixed regime of lubrication with either decreased size of film, and then the worst beast that we may encounter in lubricated systems is the boundary lubrication, where essentially there's no film that supports the contact of the two surfaces, and it is the interaction with the asperities that is playing the main role. And of course, all this action is taking place is accompanied by production of heat, and the heat changes the properties of the lubricant and makes the problem even more complex. So it is essentially a coupling mechanism. Tribology and dynamics are very, very close in those problems. Very briefly, in those slides, I'm presenting some systems where the transition from perhaps hydrodynamic conditions up to boundary lubrication conditions is taking place during one cycle of operation. One complete rotation of the crank, or one complete meshing cycle in helical gears or hypoid gears, depending on the size of the load that is transferred. So here we have the secondary motion of the piston, the secondary lateral tilting motion, which in the presence of some lubricant here is interacting with the cylinder wall, and due to the primary motion we have some friction generation, again also accompanied by occurring impacts. How much friction will be generated depends on the size of the film of lubricant between those two surfaces here. And this is a typical contour that we take if we unwrap the piston skirt surface by solving a two-dimensional Reynolds equation. For more information, I'm providing some representative papers here, and also my colleagues Nick Morris and Nader Dolatapadi, guys please raise your hands, are here to answer any questions that you may have. Similar type of problem we were encountering when we're studying the compression ring tribodynamics. So the ring here that is supporting a part of the load is presenting deflection in two planes, in the out of its plane and in the in plane of motion. And here the ring is surrounded again by some layer of lubricant. Now, because of the primary motion that the ring encounters, we have regions along its width when we have the formation of a full film, layer of film, regions where the pressure is lost and we have vapor and cavitation and then the reformation of that film. And we have the in-plane and out-of-plane motions which have to be solved interactively with the lubrication in order to get a more accurate answer about the power that we lose, the energy that is lost during one cycle. In similar fashion, for big end bearings, it's the dynamics of the shaft that need to be integrated with some computational fluid dynamics here to tell us what are the regions of high pressure, what are the regions of cavitation, and sum these up when calculating the frictional losses when we have all the cylinders operating or we have any cylinder deactivation effects. In transmissions, which is very closely related to the subject of this event today, when somebody wants to study noise vibration enhancement problems like gear rattling in the areas of the unloaded gears, then we may have separation between the pinion and the gear and single-sided impacts, or under severe scenarios we may have double-sided impacts. But all those phenomena are taking place in the presence of some lubricant between the teeth contacts. So it is the primary and secondary, the fluctuations of the rotational dynamics of the gear teeth that have to be captured and combined with either hydrodynamic or elastohydrodynamic conditions to tell us the information, to give us the accurate information about the lubricant in the contact. And if we have higher loads that are transferred, then it's also the lateral motion or tilting motion of the shafts that needs to be taken into account, and this needs to be integrated with this rotational motion in order to calculate more accurately the size of the film thickness in the contact. What I would like to focus today is a study of a rather elaborate problem of hypoid gears in rear axles from noise vibration and harshness and efficiency perspective. And I would like to show some of the main steps that we followed. Again, my colleagues Mahdi Mohammadpour and Leonidas Paouris, who work in this area, are here to provide more information during the break. So it all started as an axle wind investigation. And naturally, the noise in the cabin was captured and it was correlated to the vibration and noise in the vicinity of the rear axle. It was not only that, though. An attempt was made to capture the temperature, the bulk oil temperature here in the differential. And by comparing the severity, the amount of energy that was carried by the main frequencies that were observed in the corresponding wavelets during post-processing, we were able to match a change in the energy content per frequency as the temperature of the fluid was increasing from 40-something Celsius up to about 70 Celsius. So we identify that clearly those different mode shapes, which someone can visualize much better with a complete driveline model, doing some macro scale study, they carry different amount of energy when the temperature of the lubricant here is changing. How are those mode shapes excited, like that S-bend or butterfly mode shapes? Because of the engine orders that are penetrating the hypoid gear set and because of parametric excitation here, because of the change of the geometry and the static transmission error of the hypoid gear. So besides a macro scale study, a micro scale study is also essential to tell us what is really happening here in the box and how the lubricant behaves. So how the contact between the various pairs of teeth that are in mesh simultaneously is changing both in shape and also in orientation during the progression along the meshing cycle. And what is the relation of this shape and orientation with regard to the direction of the lubricant during this meshing process? So a gear pair model is essential. to capture these characteristics. And then the gear per model can be as elaborate or as simple as we wish it to be. For example, for noise vibration and harshness studies, it is important that somebody utilizes the change in the geometry here and the change in the meshing stiffness during one cycle, because due to the high loads, it is the solid that is suffering more compared to the lubricant. If someone wants to look at efficiency and wear, then a full numerical model that employs two-dimensional solution of Reynolds equation is needed to give us information about the pressure distribution along those contacts and the associated film thickness in that area. So this is more or less the solution strategy. The good news is that with simpler either analytical or extrapolated equation, we can directly couple dynamics and tribology and solve them in real time. But with a fully numerical two-dimensional Reynolds equation solution, this is not possible, because then we'll have to wait for a couple of years to get a solution for one complete simulation. But quasi-statically, we can get very useful pieces of information. So certain motions that contribute to the problem, like the lateral motion of the shafts, of course the rotational motions here, and the load, the resisting load due to aerodynamic force, rolling resistance, and gravity were included, as well as any engine harmonics, any engine fluctuations if necessary. Again, we consider that during cruising, the engine provides all the necessary power to overcome the resisting torque in the wheels. And that can be solved in two ways, as a steady state problem or as a transient problem. Tooth contact analysis. Another piece of bad news is that hypoid gears are not characterized by we cannot use any analytical equations to describe the geometry of hypoid gears. So we have to deal with that using tooth contact analysis. And what is important here is to capture the change in the geometry radii as we are moving along the meshing cycle, as well as the change in the meshing stiffness. Since they are both depending on time, then they can be expressed as Fourier series, where we are producing the number of Fourier coefficients that are essential in order to represent these variations effectively. And I promise this is the only equation that I have in this presentation. The other interesting feature is that during the meshing cycle, the load, the amount of load that these poor guys have to carry is changing dramatically. That has an effect on the change of those coefficients. That has an effect on those coefficients of those Fourier series here. So it is, again, very useful to update in real time our model according to the load that the pair of gear feels in order to have the actual rigidity and actual shape of contact in real time. So we have all those interesting and unavoidable, in most of the cases, non-linearities here. So we have the meshing stiffness variation, the contact radii, time variation, the static transmission error, again, a byproduct of tooth contact analysis, and the backlash non-linearity, the gap between the teeth, which are integrated in the model, and we can produce plots that describe one of the most interesting variables for noise vibration and harshness problem, the dynamic transmission error. So we can produce plots that give us the maximum and minimum values of the dynamic transmission error. How? By changing the resisting torque or the speed. The two are related, the two can be related, and recording the maximum and minimum values of the dynamic transmission error from time histories at steady state domain. And then we get graphs like this one here, where as the speed of the vehicle increases, then we notice that we are crossing three distinct regions of resonance. And each region of resonance corresponds to a different amount of energy per motion. So here we can see that, for example, we have a significant amount of rotation compared to lateral motion, in contrast to the second and third resonance, where the lateral motions are dominant. However, we see that we have in this graph much more contribution in dynamic transmission error, naturally in this area that is dealing with the rotation of the gear pairs, which is a different piece of news compared to the lateral motion here. Lateral motion, of course, is more pronounced at the areas of the corresponding resonances, and lateral motion is combined with the bearing characteristics at the supporting shaft to give us the occurring loads that can be used in a separate bearing analysis for wear purposes, losses, etc. I've talked about steady-state analysis, but what also is of significant interest is how the dynamic transmission error, how NVH behavior changes and efficiency changes during parts of those driving cycles that our colleagues have explained very nicely in the earlier presentation. And for a maneuver of acceleration, starting from the second and finishing at the fourth gear, we can see that we don't have time to reach steady-state solutions, and the fluctuations of the dynamic transmission error are significant, and they are governed by the engine orders and the meshing frequency, harmonics, and sidebands around those. So far, we talked about motion, dynamics. Okay, where is the efficiency? We capture parts of the dynamics. We capture a few meshing cycles here, and we're interested on the loads that the two gears are carrying. We're interested on the load, more importantly, on the load per tooth pair. So we can see that how different is this load fluctuation for a gear, for a pair of teeth at 120 kilometers per hour and a pair of teeth at 20 kilometers per hour. And in contrast to the static change of, quasi-static change of load at 120 kilometers per hour, as this is produced by some tooth contact analysis software. Using these pieces of information, we can solve the full numerical Reynolds equation and produce information about the pressure distribution along those ellipses per snapshot. I mean, the more snapshots somebody takes during the meshing cycle, the better accuracy we can have for efficiency calculations. And not only that, but similar sort of information somebody can obtain for the film thickness, for the gap between the gear teeth. We can see cross sections of those pressure contours here for different positions during the meshing cycle, AA, BB, and CC. And we can see that in contrast to the classic Hertzian solution, which is depicted here, we have the characteristic elastohydrodynamic lubrication spike, which is bad news for the gear surfaces, really. They are suffering at this position here. While what I was talking about earlier regarding the rigidity of the lubricant compared to the rigidity of the solids is confirmed here in those two graphs that have been obtained for two different loads of approximately 1 order of magnitude difference. Here we have a graph that was obtained for about 517 newtons load, and here we have 5,700 newtons load. So we can see that the pressure changes significantly, but the film thickness in this cross-section doesn't change significantly, only from about 1 micrometer to 0.85, 0.87 micrometers. So the lubricant is behaving as practically an amorphous solid. This information about the film thickness is important to give us the part of friction that corresponds to the viscous action of the lubricant. While in the lab, we are measuring the characteristics of the surfaces of the gear teeth. And using CMM machine, we get characteristic variables that allow us to represent those surfaces in our models with some approach like Greenwood and Tripp. And this is the part that contributes to the boundary friction lubrication. So when we put the two together, the information for the size of the film for each one of the pair of teeth that are in simultaneous contact. And here is the film thickness for a pair that is just entering the meshing cycle. Now it becomes the second teeth, and now it's about to leave the meshing cycle. We combine those two types of friction in order to get the inefficiency per tooth pair. So again, we have the inefficiency for the middle one, for the first one, and for the third one. And then we're summing up those guys in order to get information about the total inefficiency during meshing for steady state conditions or for transient simulation. And I would like to finish with this graph, which shows the friction per, the friction as we change the speed of the vehicle during steady state conditions. You remember those three resonances that we saw earlier, that were referring to the dynamic transmission error. Here they are. We have the first resonance in this region, the second one, and the third one. But what we can see here is that during resonance, we have loss of friction compared to regions just before the resonance. Why this is happening? The answer is here. We have continuous teeth contact before the resonance, and we have interruptions, loss of teeth contact during resonance, as you can see here in those gaps, for considerable amounts of the meshing cycle. Now this is leading to some kind of paradox, a contradictory observation here, which is telling us something about noise vibration enhancement versus efficiency. That we always need a certain amount of friction because friction is acting as a damping mechanism in the system essentially. But how much friction we need in order to achieve optimization between noise vibration and harshness and the power loss is something that requires careful study about the effect of the various system parameters on it. Here is the frictional energy loss during one meshing cycle before resonance and at resonance. So we see that we're losing much less energy at points B and D, which have been captured during resonance. And I would like to close my presentation with the main point. It is important to integrate dynamics and tribology. This is what we believe in a type of analysis that is commonly referred as tribodynamics. And as a colleague of mine says, has nothing to do with tribes. The two approaches are solved interactively due to their strong physical relationships. If we look at the dynamics separately, then we can get very useful information about NVH. But tribology, frictional studies, they're telling us a lot about energy efficiency of the system. And in order to have accurate input for the latter, then we need to have accurate output for the dynamics. And this is where the coupling comes. Thank you very much.